Pre-calculus students, welcome to your 8.1 notes. Today is the start of a really interesting unit on sequences and series and other number situations. But today's unit is kind of a weird one where it combines a whole bunch of ideas, and we sort of get a big picture, and then we'll sort of narrow it down and learn things a little bit at a time. But for now, it's time to get started. Let's go. An infinite sequence is a function whose domain is the set of positive integers. The function values a sub 1, a sub 2, a sub 3, etc. are the terms of that sequence. If the pattern stops at some point a sub n, it is called a finite sequence. So finite, of course, means it's ending. Infinite, it's not ending. All right, let's write the first four terms of the sequence. These are pretty straightforward. You just can think of them as like a functional notation when you see a sub n. So our first term would be a sub 1, and we could find that by just simply doing 3 times 1 minus 2, which of course would be 3 minus 2, or just simply 1. If we did a sub 2, we'd get 6 minus 2, which is 4. And a sub 3 would be 3 times 3 minus 2, or 7. You'll notice the 3n leads to addition by 3 on each step. So keep looking for those kinds of patterns. Here's another pattern we'll run into on number 2. A sub n is equal to 5 plus negative 1 to the n. Now you have to think about powers of negative 1. So if we have a sub 1, that would be 5 plus negative 1 to the first. That's just 5 plus negative 1, or simply 4. But when we go to the second term, 5 plus negative 1 to the second would be 5 plus 1, or 6. And then when we get to the third term, the pattern is going to repeat, and the fourth, it's going to go back. And I also just now noticed that I only wrote 3 terms instead of 4 on number 1, so I'm adding it. Okay, so there's the first 4 on number 1, first 4 on number 2. Again, number 2 is a little bit of a weird one just because it's an alternating sequence, but it's something that we run into, and that negative 1 to the end is going to come in handy later actually too. Okay, write the expression for the nth term. So this is going to be essentially pattern identification. So if you look at number 3, you can see each time we're adding 3. I saw that actually on number 1, so I know it's going to be an a sub n is equal to 3n situation. But then the other thing you might notice is when we have 3 times n, our first term would actually be 3. We're 1 behind that, so I sort of have to adjust a little bit and make it match up exactly with what we have. So 3n would go 3, 6, 9, 12. 3n minus 1 drops all those numbers down by exactly 1, and that's our pattern. Okay, we have a little bit different pattern going on number 4. You might recognize it though. Each time when we go from 3, and I'm going to ignore negatives for now, I'll come back to that, but 3 to 9, 9 to 27, and 27 to 81, we're multiplying by 3 each time. So that would be not a 3 times n, but actually a 3 to the n power. Okay, so 3 to the first would be 3, 3 to the second, 9, 3 to the third, 27, and so on. The one issue, and I said we'd come back to it, now is the time, we have alternating signs, positive, negative, positive, negative. So what I'm going to do to fix that is I'm going to put over here in parentheses a negative 1, and I'm going to raise it to the n plus 1 power. Now you may be asking, why n plus 1? What is n plus 1? What does that have to do with this problem? Well, the n power would be the correct pattern, but we would have the terms exactly reversed, where we would be seeing we would see the first term negative, then positive, then negative, then positive. So negative 1 to the n plus 1 flips that. So now the first term would be negative 1 to the second. That's just 1 times 3. All right, and we'll see the alternating signs. As a matter of fact, even the next problem has it. But we will definitely see that from time to time throughout this unit. Okay, number 5. This is kind of a weird pattern, and it may not be one you immediately notice. Again, I would suggest ignoring negatives and just think about it as 2, 5, 10, and 17. But here's kind of the pattern I'm seeing. Again, ignoring negatives, we're going plus 3, plus 5, plus 7. You can imagine the next term would be plus 9. Anytime you see consecutive odd numbers being added, you actually have a different pattern going on. This is actually a perfect square pattern, close to perfect squares. Now think about it though, if we listed the perfect squares, we'd have 1, we'd have 4, 3 squared would be 9, 4 squared would be 16, and that pattern would continue. Now you'll notice that we are close, but everything is off by 1, so we're going to adjust for that situation. And here's how we can do it. We're going to do n squared plus 1. That's going to take care of 1 being 2, 4 being 5, and then 10 and 17. The only thing we haven't dealt with yet is the alternating signs. We're going to do it the same way as we've done on number 4 and what we saw on number 2. And this is the scenario where we want the first term to be negative. So we want negative 1 to be raised to the n power. All right, let's move on to the next slide. And we have a weird situation here. You wouldn't expect to talk about rabbit breeding when you walked in the door today for your math class, but that's what we're going to do. So here it is, the Fibonacci sequence, and the definition is a sub o, that means the beginning term of the sequence, is the 0th term of the sequence is 1, first term is 1, and then essentially a sub k is equal to a sub k plus minus 2 plus a sub k minus 1, where k is greater than or equal to 2. Let's actually go through and talk about that, because that terminology right now may not make a lot of sense to you. It'll come together in a bit. Okay, so even though this was first found in India, in the West, the Fibonacci sequence first appears in the book Liber Abaci, and apologies for my terrible Italian pronunciations, by Leonardo of Pisa, known as Fibonacci. Fibonacci considers the growth of an idealized rabbit population, assuming that a newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of exactly 1 month, so that at the end of the second month, the female can produce another pair of rabbits. So rabbits will never die. Again, we're saying idealized here, not realistic. And a mating pair always produces one pair that involves a male and a female every month from the second month on. And the puzzle that Fibonacci posed was, how many pairs will there be in 1 year? Now, when you can get over the fact that this family tree of rabbits is not forking, we can actually think about this mathematically. So let's think about it this way. Let's think about what month we're in and how many pairs of rabbits there would be. We have to think of it in terms of pairs, not just single rabbits, for this to make sense. So we know in the first month, and really I should start it this way, the 0th month. Now why am I starting there? Because this is where we begin. Okay, now 1 month later, we still have exactly one pair of rabbits, because the first pair is now mature. They started as infants at time 0. Now they're a month old. So now they're mature and they're ready to add to the family, let's say. All right, and the new pair will be born at the conclusion of the second month. So now we've gone from one pair of rabbits to 2. Okay, very cool. All right, now when we go into month 3, what's happening is that first pair of rabbits is immediately able to reproduce again. Gross, but it's the way it works, I guess. And then the baby pair is not able yet, but at the end of a month they'll be ready to begin that process. So we will now have the 2 pairs we already had plus the original pair just made one new pair, so now we're up to 3 pairs. When we get to month 4, now the original pair plus the first babies are now reproducing, so we're up to 5 pairs of bunnies. And the where are they? In the field? In a field. In a field. There it is, just in a random field. Okay. Now what happens is when we get to month 5, we've still got the 5, but 3 more are able to reproduce, the ones that are at least a month old. So that's going to give us 8. At month 6, you'll have the 8 that you already had plus 5 new pairs of babies. And so, not 5, but 13. Now what you'll notice is every single month essentially what we're doing is just adding the two previous numbers to this sequence. So after 9 months, we're at 55. At 10, we'd be at 89. At 11, 89 plus 55 would give us 144. And then finally, at 12 months, 144 plus 89 would be 233. We would have 233 pairs of rabbits at the end of 1 year. And as weird as that problem is, it's kind of an interesting sequence. So even though, where it's not really the greatest thing to think about, it is an interesting study in what happens when, what this Fibonacci sequence looks like and how it increases in size. Okay, now Fibonacci sequence is just one example of a recursive, so we're going to look at some other recursives. Things to remember with a recursive, you're always going to have a formula like an a sub k plus 1 equals kind of thing. And you're also going to always have to have the starting point, a sub 1. Now this says to list the first 5 terms in the sequence. Well, the first term is given to us. It's 7, so that's easy enough. If I want to find the second term, what this says to do is take the first term and subtract 4. So that's 3. Let's talk notation again. The second term would be a sub 2. A sub 2 is the first term minus 4. And I would continue on that process as many times as I needed to. And this says to find the first 5, so I'm going to stop right there. Okay, so essentially this is saying a sub k plus 1 comes from taking the previous term, a sub k, and subtracting 4. So any term I want to find, I have to know the term right before it, and then I just simply subtract. Okay, here's another example of a recursive. Again, the first number is given to us, it's 2, and this tells us to take the previous term, which would be 2 in this case, and multiply by 3. So essentially all I'm doing here is just taking the term that I have, and I'm going to multiply by 3, and my fifth term would be 162. There's the first 5. All right, let's move on. We're going to learn about something called factorials today. And maybe I should say it with a little more excitement. Not just factorials, but factorials! Okay, sorry, I tried. All right, so a factorial is, yeah, a little exclamation there. But the definition of n factorial is essentially we take every integer that's in or the numbers below it down to 1 and we multiply them together. So for example, 1 factorial would just be 1, where 5 factorial would be 5 times 4 times 3 times 2 times 1, or 120. And then there's a weird one, 0 factorial is 1. I want to talk about that for just a minute so you can kind of see that pattern. I'm going to start with some things that sort of make sense, I think. 1 factorial would be 1. 2 factorial is 2 times 1, so that would be 2. 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial would be 4 times 3 times 2 times 1, which would be 24. And I'll do one more. 5 factorial would be 5 times 4 times 3 times 2 times 1, which would be 120. Okay, so essentially, to go from 1 factorial to 2 factorial, I multiplied by 2. Then to get to the next one, it was times 3, times 4, times 5. Now, if we reversed that, you could think of it this way. Divided by 5, divided by 4, divided by 3, divided by 2, and then the last one, of course, would be divided by 1. So 0 factorial, and this may be a bit of a surprise, but it's equal to 1. That's one we just have to keep in mind. We actually, somewhat surprisingly, I guess, we'll run into that a lot in a lot of the probability work we do. So you definitely want to have that one available in your brain. 0 factorial, that's 1. All right, let's do a little simplification. Now, there is no reason for me to do 17 times 16 all the way down and multiply it out. But for this one problem, and this one problem only, I'm going to go ahead and write it out. Now, I'm not going to actually multiply these, and I would discourage you from doing that either. And I'm kind of wondering why I'm doing this the more I think about it, but I've begun, so let's finish the job. So 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That right there is 17 factorial, and I know I had to use 2 rows, but I'm running out of space, so I have to adapt. All right, now 15 factorial would be 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 and 6 and 5 and 4 and 3, 2, and finally 1. Okay, why did I do all that? To show you that if all these numbers are multiplied together and all these numbers are multiplied together, the 15s will cancel, 14s will cancel, 13s, 12s, 11s, 10s, 9s, 8s, 7, 6, 5, 4, 3s, 2s, and 1s will all cancel. And essentially what we're left with is just simply 17 times 16. Now that's still a fairly large number, but 17 times 16 is equal to 252. So please don't spend the time multiplying all these numbers together. Instead, think about how can I simplify it. That's what we're going to do on all these. We're going to simplify them. All right, here's your next one. 8 factorial over 2 factorial times 6 factorial. So here's the way I'm going to simplify this. I'm going to rewrite 8 factorial as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm going to actually stop right there. Okay, and I stopped at 6 factorial because we have 6 factorial in the denominator. 2 factorial we know is just 2 times 1. If you want to write the 1, you can. And then 6 factorial is still just 6 factorial. And you'll notice right away that the 6 factorials cancel each other out. We're left with 8 times 7 divided by 2 times 1. That's just, I'm just going to call it 4 times 7, which would be 28. All right, now this last one here is honestly the same kind of patterns that we've used on the others, except we have variables rather than just numbers. So when we think about n factorial, n is just some integer value. So it would be n times n minus 1 times n minus 2 times n minus 3, all the way down till we get to 1. So I'm not going to, especially since I don't know how big n is, I'm just going to stop and say it's n times n minus 1 factorial. This is also n minus 1 factorial. So those two terms, n minus 1, goodbye. We are left with n as our solution. Okay. Anytime you have these variables, these are always ones that provide a little bit of a challenge. So make sure you kind of you have to think about which number is bigger and just start simplifying that number until you find the other one. All right. And don't worry, we'll practice plenty of those. Earlier I mentioned that this particular section is a bit of a hodgepodge where we throw a lot of like terminology and notation at you. Well, here we are with another one. This is called summation notation. This funky looking E is a Greek letter called sigma. Okay, so you might see this called sigma notation at times or summation notation. They work the same way. All right, summation notation. We have the definition here. This says from I equals 1 to n of a sub I, that's a sub 1 plus a sub 2, a sub 3 plus, and then you add till you get to a sub n. Let's do this with some numbers that I think it might make a little more sense. So here we go on number 11. This is the summation from I equals 1 to 5 of 3i. The summation of I equals 1 to 5 of 3i. So the first thing I'm going to do is plug in 3. So I'm going to have 3 times 1. I'm basically where I have an I, and don't confuse that with the imaginary unit, by the way. It's just a variable. It says I equals 1. And you can use k, you can use x. It really doesn't matter what's there, but I used I, so there it is. All right, so we do 3 times 1. Then we do 3 times 2. And you'll notice that I'm adding these numbers together. We're adding them because it's a summation. Okay, so that implies that we are adding or finding the sum of all these numbers. And we stop when we get to 5. Okay, and so this would be 3 plus 6 plus 9 plus 12 plus 15, and that would be 45. Okay, so that is the finished answer there, the sum of I equals 1 to 5 of 3i. You just plug in 1, 2, 3, 4, and 5, and then find the sum of all 5 of those numbers. Let's do another one. This is the sum of I equals 3 to 5 of I squared minus 2. So I'm just going to plug in these three numbers, 3, 4, and 5, and we'll do a little more mental math this time. 3 squared minus 2 would give me 7. 4 squared minus 2 would give me 14, and 5 squared minus 2 would give us 23. If we add those together, we get 44. Okay, we've got one more we're going to look at. This one has 9 terms. This is a bit of a pain, but we'll go through it together. We're just going to go from I equals 0 to 8 of 1 over I factorial. So here we go. 1 over 0 factorial would just be 1 over 1. 1 over 1 factorial would also be 1 over 1. Then it's 2 factorial. 3 factorial gets us to 1/6. 4 factorial, 1/24. 5 factorial would get us to 120 in the denominator. 6 factorial would be 120 times 6. That would give us 720. 7 factorial, 1 over 7 factorial is 1 over 5,000, excuse me, 5,040. And then we multiply that number by 8, that denominator by 8, and we get 40,320 in our denominator. Okay? A little weird, a little ugly. Now, I'm not going to ask you to do this kind of, addition in your head, but I've used my calculator and I got this number, 2.71828 approximately. And you might notice that that number looks somewhat familiar. It's E. How cool is that? All right, so E shows up again when we least expect it. So a sum of 1 over I factorial, and if you continue this infinitely, we would get exactly E, but in this case, we're just getting an approximation because we stopped after 9 terms. Maybe it's just me, but that's pretty cool. Okay, next thing we're going to look at is similar to what we were just looking at, but sometimes we have infinite sequences. We can call these series, and of course you can't add an infinite number of numbers, but you sometimes can, weirdly enough. And I know that sounded really contradictory, and it sort of was, but you'll see what I'm saying in just a second. You can find patterns, and a lot of times you can actually figure it out. Okay, now this says to find the third partial sum of the infinite series, k equals 0 to infinity of 1/10 raised to the k power. All right, so we're going to do the third partial sum first. That's going to be our first objective. So the third partial sum, what that means is find the sum of the first 3 terms in the sequence. Okay, so if I do the first 3, k is 0 is where we start. 1/10 to the 0 would be 1. The second term is when k is 1, so 1/10 to the first would be 1/10. And then the third term would be actually when k is 2, so 1/10 squared would be 1 over 100. Okay, now if you wanted to think about how to add these together, we could do it with fractions, but I think I'd rather actually in this case look at the decimal version of each of these numbers. 1/10 is 0.1, 1/100th would be 0.01, so what we get there is 1.11. Okay, that is right there our third partial sum. Now this says to find the third partial sum and the sum. So what we have to do to find the sum is we can't literally add an infinite number of numbers together, but you can think about it for a minute. Okay, well, what's happening? Well, every single time we go another place down the line, we're adding another 1 to our decimal. So it's going to be 1.11111111, and that's going to repeat infinitely. So the sum is 1.1 repeating. Now some of you may recognize 1.1 repeating, or well, specifically 1 repeating is 1/9. So 1 and 1/9, or 1.1 repeating, would be 10/9. So we just added an infinite number of numbers together. All right, I believe this is the end of the road here, this slide. We're going to use sigma notation. So in this case, what we're going to do is actually, we're going to write the sequences, the sigma notation version of these sequences. Now I'm going to actually write both of them out, and then we'll come back and take a quick look at the calculator work as well. All right, so let's start with the first one here. And I'm going to have the summation of, and I'm going to use k. I like using k on these, but you can use whatever variable you want. You can use n, you can use I, choose a letter, whatever. All right, so I'm going to do k equals 1 as my starting point. And the reason I'm doing 1 is I'm looking at this pattern and saying numerator stays constant. Denominator is always 1 plus. And you can see that number goes 1, 2, 3, and so on to 12. So I'm going to do k equals 1 to 12 of, my numerator is going to be 2, my denominator is simply going to be 1 plus k. So instead of writing 1 and 2 and 3 and 4, I'm saying it's whatever term you're on, use k. All right, so there's our sequence for number 15. Again, we'll come back in a moment and actually punch these in the calculator. Okay, this sequence on the next problem might actually at first glance look a little more complicated to you. But let's look at this one term at a time. Now, first of all, I'm going to look and say, well, I have 5 terms. So I'm going to use n this time. So n equals 1 to 5. Okay, piece of cake. Going from 1 to 5 because there are 5 terms. Let's look at numerators and denominators separately. I think you might recognize this pattern in the numerator, 3, 9, 27, 81, 243. We actually saw that earlier in the notes. It's just powers of 3. So I'm going to write 3 to the n in the numerator. Now, denominator, you might not before today have recognized this pattern right away. But let's look at it today. Now we know 1, 2, 6, 24, 120. Some of you may already be thinking in your head, I know this one, I know this one. This is your factorial. Be excited. You figured it out. All right. Now, let's go ahead and take a look at, we'll look at both of these and how we could approximate both of these on the calculator. So I've dragged my calculator over now so we can walk through these two pretty quickly together. So if you go into the alpha buttons, and we've done like matrices, but if you go over to F2, alpha and F2, it's above window, you will notice that option 2 says summation. And now on mine it even has a little symbolic notation so you can see what it's going to look like. And I'm going to go ahead and choose option 2. Now, I know I chose the letter N, I believe, but I'm going to just use X because it's easier to type that variable in. So I'm going to do X equals 1, and I'm going to arrow up and do to 12 of, and then I can do 2 divided by, and if you want to use the fraction bar, that's fine. I'm just going to simply use parentheses to group this, and I'll have 1 plus X. So this is 2 over 1 plus X. You can close or not close those parentheses. It's personal preference. Don't know why that thing ended up so big. Uh-oh, what did I do wrong? I must have a parentheses issue. Oh, I hit parentheses twice. That's what happened. All right. Even I make mistakes. Who knew? All right, so there's our first one. We get about 4.36. I'm going to enter the second one as well. Again, this alpha and F2. And option 2 is the way to go. And this time our sequence went from 1 to 5. So I'm going to go X equals 1 to 5. And again, you can use any letter you want here. I just like X because I don't have to hit the alpha button and go hunt for it. I can just simply easily type X, the variable button. And I'm going to use the fraction bar this time. Just, it doesn't really matter. So the numerator we said was 3 to the X. And the denominator is x factorial. Okay, now some of you may be saying, now wait a minute, where is that factorial button? Now we're going to be honest, it's not one that you're going to probably use every single day, but obviously today is one of those days. And for the next time being, we will use them. So if you go into your math menu and you go over to prob, it's probably there. All right. As a matter of fact, I know it's there. It's probability. and there we go, factorial is found. Okay, I don't think there's an easier way to get it, but if you find one, just go ahead and share that with your neighbor if you find an easier one. More importantly, share it with me so I know a faster way to get that factorial. As a matter of fact, it's probably up on those alpha buttons somewhere. All right, now mine says 87/5. I have a weird mode where it's automatically going into fractions. But most of you, I would imagine your calculators at this point probably say 17.4. I believe that'd be the number. So we've got our two values, 4.36 on the first one, and again about 17.4 on the second. Hey folks, I hope these notes haven't been too long. I know they've been kind of long, but thanks for sticking with me, and hopefully you pick this stuff up. Don't panic if there are some things that are still a little hazy for you, because as we move forward, we'll revisit virtually every concept we've seen on the notes today, and we'll get better and better at it as we move along. So do your best on today's assignment to find those patterns, recognize them, and use the correct notation. You all have a fabulous day.